All right, so I've had this on the screen before. And when we finished the midterm, we said, okay, now we're going into, we did derivatives, rate of change, f prime, f double prime stuff. And now we're going to look at the other half of calculus, elementary calculus, beginning calculus, whatever. Yeah, I hate using that term. It seems kind of like an oxymoron. Then elementary calculus, basic calculus. But it is the case. I mean, that's what it is. It's derivative, the two main components, derivative and the integral. And so we talked about the definite integral. We talked about how it's area under the curve, and we did that example of if we knew how fast we were going at 1 minute increments, we could figure out about how far we travel. We could estimate how far we travel. We talked about how we wouldn't know for sure because we don't really know in between those 1 minute or 1 second intervals how the speed was changing, right? But so we talked about how the area could give us the distance, the area under velocity. That's the example we've used the most. The area under the velocity could give us distance. And so we talked about that with rates. So, matter of fact, maybe I should look at this first. On that sample 2 packet that you were supposed to be looking at today, I was going to look at this problem right here. And so maybe you want to pull that out. So as I write this down, you can jot it down because you may not have gotten this one. This is number 43. But it's related to where we're headed with this, at least as far as giving us a look ahead a little bit at why we're so interested in these integrals, right? I mean, remember how we ended up with derivatives. We ended up in chapter 4, which were applications of derivatives. What are all the ways we can use derivative? We did slope fields, we did related rates, we did optimization, we did L'Hopital's rule, we did all these different kind of uses of application, story problems, kind of ways the derivative can tell us things. Well, we want to get to that same point with integrals. We're going to get there faster, and quite honestly, I think they're easier than derivatives. I think the problems we do with integrals are easier to set up. And here's a perfect example. Now, we have a ways to go, a little ways to go yet in the understanding of why we do the integrals, but we've got a little bit of an understanding, I think, already. We've done a problem similar to this. It says a tank is being filled with water at this rate. Gallons per hour. T is measured in hours. If the tank is originally empty, how many gallons of water in the tank after 4 hours? Will anybody have an idea of how we could go from gallons per hour to gallons? Antiderivative. Now, we could do this 2 different ways. We could call this function f prime if we wanted to, because isn't it a rate? So we could say f prime is 300 t to the 1/2. Would that be correct? So we want f, the gallons. So what did they tell me right here when they said the tank's originally empty? Well, yeah, I want to write it this way because it doesn't mean C is 0 necessarily. I think it's going to be in this problem. But it really means f of 0 is 0. Because if f is going to be gallons, right, if f prime is going to be gallons per hour, then f is going to be gallons. So the amount of gallons at time 0 was 0. So it's like an initial condition. So really this is like an IVP, we call it, initial value problem. It's a differential equation, right? It's an equation with a derivative in it, and then an initial condition, right? I mean, that's what it is. I mean, so you see these connections between all these things we've already done. So could we find f? Sure, antiderivative, right? Just got to approximate. Raise that up to 3/2. Divide by 3/2, which would be 2/3. What's 2/3 times 300? This is actually a calculator problem, but let's just pretend for right now it wasn't. 200. So this would be 200 t to the 3/2 plus some c, right? But since we have our initial condition, we could put a 0 in here, and we get 200, 0 to the 3/2 plus c's got to equal 0. Well, we know this is going to be 0. So like Emily said, c is actually 0. But it wouldn't always be, right? I mean, you could put 0 into some things and not get 0. So we know that our gallons function is 200 t to the 3/2, right? So what do they want to know? How many gallons we have in 4 hours. So what do? Plug in a 4. So you plug in a 4. The square root of 4 is 2. 2 cubed is 8 times 200? 1600. So f of 4 is 1600. So it actually is one that could have been done, right, without a calculator pretty easily. Now, let me do this in red. Let me show you how integrals, so antiderivative we can do, but here's going to be the problem. Here's where integrals, and this relates to what we're going to be doing starting today. Integrals involve antiderivatives. They're not the same, but they could be, right? When you do an integral, one way to do a definite integral is to do big F of B minus big F of A, right? Do an antiderivative and do that. Well, here's the other way we could have done this problem. We could have simply set up this integral right here. You see why that would be the same thing? Because inside there is gallons per hour, and when we do the integral of gallons per hour, it turns to gallons, and we want the gallons from 0 to 4. Now, there is a slight difference. There's a slight difference here in the sense that this, and this is something we'll work on over time here, but this actually gives us the net change in gallons over those 4 hours. But won't, in this problem, that also be how many gallons are there at 4 hours? This is really the amount of water that went into the tank over that 4-hour period. But since the tank was what? Empty at the start, this integral actually gives us that. And now on our calculators, we can actually just go in, and since this is a calculator problem, we can just go type that in. That's one of the things that we'll set up these integrals, and then we'll just get to type them right into our calculator. It's going to give you 1600. A lot less work than doing the other way. Now, if we were going to actually, if this was no calculator, we'd have to do big F of B minus big F of A. So we'd have to do our antiderivative, and we would do 0 and 4. We plug in a 4, we get 1600. We plug in a 0, we get 0, right? I mean, so we could do it without a calculator too. Do the antiderivative. Okay. So that gives you a little sense of the type of problem, type of story problem we're looking at. Pretty easy one, really, once you understand that, hey, gallons per hour, I want gallons. That's an integral. Antiderivative, boom, set it up. There you go. Okay, then we do it. Now, if there's no calculator one, we got to be able to do it like the gateway test. If we struggle on the gateway test and we didn't study our antiderivatives and we can't do antiderivatives, that's going to be a problem. That's going to be a problem. Okay, we'll do good on the calculator ones, and no calculator we might not do as well. So we got to be able to do that. So you can see why we've studied, because it gave us the answer to this problem. But what about the definite integrals that don't have antiderivatives? And that's what we're going to get into now. So, back to these notes. When we set up a definite integral, our goal here going forward is we're going to solve problems. We're going to use definite integrals to solve them just like that when we set up a definite integral. We can see the first method we did in blue. If there's no antiderivative, the first method won't even work, right? The one where we had f prime and we wrote the f equation. If there's no antiderivative, that method won't work. We'll have to do it by an integral. But if there's no antiderivative, well, that rules out that one, right? And do most functions make a geometric shape? No. So therefore, we need to be able to handle integrals where we can't do an antiderivative. And the only way then is by approximation. So we're going to investigate here, how do we approximate these areas? Okay? So, that thing that I sent you, well, here, let me type this into the calculator real quick. So, let's say I have this integral right here. We could all do this one on our own, right? We could do the antiderivative of that. And look what the calculator does. It gives you an exact answer. Why? Because it was able to do an antiderivative. So inside the calculator program, it found that antiderivative, negative cosine. It plugged in a 2. That'd be negative cosine 2 minus cosine of 0, negative cosine 0. So that'd be plus cosine 0, which is 1. So it's negative cosine 2 plus 1, which it writes as 1 minus cosine 2, right? We can all get that one. Now let me change that integral just a tad. Let me change that integral into that. There is no antiderivative of that function. But there certainly is an area. If we graphed sine of x squared, there'd be an area from 0 to 2. How do we find that area? Well, the calculator does it, but look what answer it gives you. What's that tell you that the calculator gave you a decimal? It's an approximation. The calculator will try. We're in auto mode in our calculator. It'll try to give you an exact answer. If you tell 2 square root of 2, it'll give you square root of 2. You have to force it to give you a decimal, right? You have to control enter. You have to force it. It's going to give you an exact answer. If it gives you a decimal and you didn't put any decimals in your problem, right? If you put a decimal in your problem, if I had put 2.0 up there, it would have given me a decimal for sure. Because if you got decimals in the problem, it assumes you want decimal answers. But if there aren't any decimals in your problem, it's going to give you an exact answer. If it can't find an exact answer, is the only time it goes to a decimal. It is getting an approximation. So one way you might think of what we're going to do here over the next number of days, how in the world does the calculator do that? How in the world did the calculator get programmed to approximate that area? And to be honest, that area is an approximation, but it's accurate out to all those decimal places as far as the exact answer. And how in the world, if there's no antiderivative to be found, can it even know what the exact answer is? How can it know it's accurate out to that many decimal places if it doesn't know what the exact answer is? That's one of the things we'll investigate over the next course of weeks. Okay? All right. So if we go to that document you guys have here that I sent you, the LRAM, RRAM one. Okay? Now I sent you this. We're not going to do anything with it. This is for you to play around with. If it helps you just visually, if you're a visual person and you like to, this would help you to look at this and drag things around, then that's why I gave it to you. So if we go to the next page, control right arrow, you can read those things. It's just telling you that you can play around with these things, change the function, do different things, and then it says enjoy. Okay? So here's a function, x squared plus 1. Does everybody look like this? Okay? And we want to do the area. We're trying to figure out the area under there from 1 to 3. Okay? Now this is one we could do. A lot of times when we're investigating these, we're going to pick functions that we could find the exact area. We're going to pick some easy ones, right? Just understand we're doing this because there are some out there, like sine of x squared, that don't have an antiderivative. Okay? So yes, we could find this exact area from 0 to 3. Matter of fact, I think, no, I guess it did give it to you. Okay? But we could figure it out. Wouldn't be hard. Fundamental theorem part 2. These are 4 rectangle areas. If you added those 4 areas together, because we know how to do rectangles, right? So the idea is, okay, we don't know what geometric shape that is. Let me go back to this thing. Okay, so right? So doesn't make a geometric shape. If we can't do the antiderivative, this is all we got left to do. Okay? So we know how to do rectangles. So I'm going to put 4 rectangles. Now these are 4 special rectangles. This is notice it says LRAM equals 8.75. LRAM stands for left rectangle approximation method. We'll just say left rectangles. Left rectangles. Now why are those left rectangles? The left endpoint of the subinterval is the height, right? Plugged into the function. Now let's talk about that terminology. The reason I said subinterval is because the interval is from 1 to 3. We're doing the integral from 1 to 3. So that's our interval. We're going to divide that into subintervals. In this case, 4, right? 4 subintervals. So what we do is 3 to 1, that's a total distance of 2. 2 divided by 4 is 1/2. So 1 to 1/2, 1/2 to 2, 2 to 2.5, 2.5 to 3, right? So at 1, at 1.5, at 2, at 2.5, we plugged into the function and we got the height. Now you guys remember when we did that, when we said if the car at 0 seconds, 1 second, 2 seconds, 3 seconds. Remember when we added those up but we left off the last one? Remember that? Because some of you added up all 6. I said, wait a minute, that's 6 velocities. It's only 5 seconds. We said pretend it was this speed the whole first time, the whole first second, and then this speed the whole second, and this speed the whole. Remember that? That's what that would be an example, right? So what we're saying is at the beginning of the subinterval, what a left rectangle does is pretends the function just stays straight the whole time. Now it clearly doesn't. So we're off. Would you call this an under approximation or an over approximation? The left rectangles are an under approximation. Okay? Now, we can move to the next page and we get 4 right rectangles of that same interval. Now, what you can do is you can drag this. You can drag, the right edge here, and you could look at here, whatever. I don't think you can change the number of rectangles. I don't think. Okay, which is fine. We're going to do that in another one. So that's an over approximation, right? But see how those are right rectangles? In each subinterval, we take the right edge and we go up to the curve. And that's our height. Right? So we can always find that because all we have to do is divide our interval and then take those values, plug them into the function, the x squared plus 1. So we don't need an antiderivative or a derivative. All we're doing is plugging those numbers into the function. That gives us the height of our rectangle. The width we can find out easily. It's just our total width divided by how many we have, right? And then that's the height of each rectangle. And then we add them up, and that's our approximation. Okay, simple. Go to the next one. MRAM stands for midpoint rectangle approximations. Notice how each of these rectangles, the height is determined by the midpoint of the subinterval plugged into the function to give you the height. Make sense? Does that look better than the other two? That's better, isn't it? Because it's got a little bit over, a little bit under, so that's probably closer. That's true. And if you were just going to do 4, you might want to do midpoint. It'd be a better approximation. Those other approximations aren't going to be as good, right? Now, what would make all of these approximations better? We did this the second day of class. What would make all of the left, right midpoints better? More rectangles, right? 10 rectangles would be better, be closer, right? 20, 100, 1,000,000. Now, if I'm doing them by hand, I don't want to do that, right? That would suck. So that's why the calculator is going to come in handy, right? Our rule is going to be this. If I ask you to do single-digit rectangles, you're doing them by hand. 4, 8, whatever. If it's 10 or more, we're going to have a program on our calculator to do it for us. If I ask you to do 10 rectangles, 20 rectangles, 50 rectangles, you'll get to do that on the calculator. So the first day, this first day's homework is going to be by hand stuff. Doing stuff by hand. So single-digit number of rectangles. Okay? Which we'll do here in a little bit. All right, is that the last page, I think? Yeah, that's the last page. Okay, now, let me show you an example here now. Same situation. Now, this time I got a function that's going up and down, so it's a little more complex function. So now if I show 4 left rectangles, some of them are over approximation, some of them are under, right? So now it's not as easy to tell, is the total here an under approximation or an over, right? I mean, I got some of this that's over, I got this that's under, I got a bunch here that's under. Probably this is an under approximation. Well, actually, we can tell right here because I got the exact answer here, right? So here's the exact area. There's my 4 left rectangles. Excuse me. Here's 4 right rectangles. These are under, these are over. Now notice it's reversed, right? When a left was under, the right was over, and vice versa. Right? Makes sense? Okay? This time it's an over approximation. Here's my midpoint rectangle. Right? Now it's much closer. Notice it's much closer, just like you saw before. So we take our midpoint and we go up to the curve. Take our midpoint and go up to the curve. Take our midpoint and go up to the curve. Take the midpoint of the subinterval, go up to the curve. Get the y value. The y value is the height times the width. You get the area. Okay? All right. Now, the other one I didn't show is trapezoids. So we talked about that first day we were doing this. Is we said, what if you averaged? Remember that? We said if you're going this fast at the beginning of the second and this fast at the end of the second, how about you average that? And that's your average speed. Right? That's what a trapezoid does. Okay? So this is better too. Notice this is kind of like the midpoint. The midpoint and the trapezoid are better than the left and the right, aren't they? Okay? So here's a trapezoid. You just go up to the curve at the left edge, and you go up to the curve at the right edge, and you connect them. That's how you make a trapezoid. Then you take the next interval and go to the left edge, go to the right edge, and connect them. Left edge, right edge, connect them. Left edge, right edge, connect them, and you make a trapezoid. Again, if we had a bunch more trapezoids, well, let's go to the rectangles. Oops, I gotta stop that. See, there's 25 left rectangles, right? Now the left rectangle is a pretty good approximation. Oh, there's 75. Oh my gosh, keep going. Okay. Okay, if you got 46 left rectangles, you can get a pretty good approximation. Okay, and we can keep going. Okay, all right. So again, how do we approximate an area? Well, we got to do it by geometric shapes. We know how to find the area. Right? So rectangles are the easiest. Trapezoids are a little more complicated, but they're better. Midpoints are rectangles, but there's always the issue of finding the midpoint, so that makes them trickier. So those are the things we're going to be looking at. Those are the things we're going to do with this. Okay, so let's move on to do this problem right here. This is number 17 in your book. So what we're going to spend some time doing here is just kind of working through what this is going to look like to actually do these calculations. Now, we're going to use notation to help us do a better job of organizing our work. Now, I'm not making you write this out because it's busy work. You know, hopefully you don't think I make you do that just to do busy work. There's a reason for why we're going to be very organized in how we write this stuff out. Okay? You're going to have homework problems that are going to be very similar like what we're doing here. Okay? So, the reason we're going to be very organized with how we do this work is that's going to lead us into some formulas, some rules. All right, cool. All right, so, it's made my day. All right, so, here's number 17. Turn in your book to section 5.6. Turn your book to section 5.6. Look up number 17. All right, and the directions say, draw a sketch that illustrates the approximations L4, R4, M4, and T4. Then compute, that's a left with 4 rectangles, a right with 4 rectangles, and so forth. Then compute each approximation and compare it with the exact value of the integral computed using the fundamental theorem. Okay, that's a lot of stuff. So I went ahead and graphed it. Okay, you can just make a quick sketch here. Now, if this was a homework problem though, and actually the homework problems we're going to do, you're going to have separate sketches, it's going to be separate problems. Okay, like problem 1 will be just lefts, and you're going to draw a picture for that. Problem 2 will be just rights, and you draw a picture for that, and so forth. I think, let me look on the homework. Yeah, I think we're going to do number 16 is going to be very much like this. So you can do a little rougher version of it right now, but on your homework, it's going to be 4 separate graphs. I want a graph of L4, R4, M4, T4. Okay? So right now, I'm going to just put them all in the same graph, but I would want, and you can do that right now, but it gets to be a mess, right, if you do it all on the same graph. So let's do the first one in, well, I've already used red there, that's fine. So let's do 4 left rectangles. So what do you suppose the first thing we have to figure out if I want to do 4 rectangles? How wide they're going to be, right? Well, how wide are they going to be here? 1. Now, the formula, if you want to memorize it, is B minus A divided by N. N is going to be the number of rectangles. But let's think about it. It's pretty common sense, right? It's going to be the total width. So that's 2 minus negative 2 divided by our 4 rectangles. So 4 divided by 4 is 1, right? So they're going to be 1 wide. Now, the term we use for that is delta x. Delta x, right? Change in x. Delta y over delta x is what we do for slope. Change in y over change in x, rise over run. Think of the width as kind of the run, if you will, right? It's how wide they are. We're going to call that delta x, our width. So our width of our rectangle is going to be 1. So that means if I want to draw a left rectangle, so I go to this subinterval, and we haven't done any of the negatives, so this will be interesting. So here's my first subinterval. It's 1 wide. Where do I go to get the height? Down from where? From which x value? These are left rectangles. So what's the left edge of this subinterval? Negative 2. So, right? So we figured out that the subinterval, they're going to be 1 wide. So I'm going to go down here, down on the -2. I'm going to go down to the function here. I'm going to go across and make myself a rectangle right there. There is one left rectangle right there. Now that area is going to be way more than my actual red area, isn't it? Right? Okay. What about my next left rectangle? So my next width is 1 right here. So my left edge is -1, so I'm going to go down to the curve to -1, and I'm going to go across. Now, probably should shade that, right? But it's going to get messy here because I'm going to do them all in one. You'll see why we don't want to do these all in one. Okay? And there will be my next left rectangle. What about my next one? It's not going to have any area at all, is it? I'm going to put a real thick line there so you can tell we've done something there. Okay? So we got 0 to 1. I mean, there's no area. There's no rectangle. Sometimes that happens. Its height is 0. And then what about the next one? Go up to +1, and we'll go across. So there would be my 4, and actually one of them is not even really a rectangle. So in black, there would be my 4 left rectangles. Okay? Now, let's write out and let's calculate the areas of those. Now, we could sit here with just scratch pad and we could just, our calculator, and we could just calculate those out. Count squares, whatever. But I want to use actual notation. This is little f right in here. We're going to call that little f, okay, the x cubed. Okay, so tell me the height of my first rectangle.
18.
-8. Remember, area below is negative. We can see why, right? The height here is -8. Now, I don't want to write -8. How did we get that? Putting -2 into the function. So I'm going to write L4 equals f of -2 times, because that's the height of my rectangle. What's the width? 1 plus, what's my next rectangle height? -1 times 1 plus f of 0 times 1 plus f of 1 times 1. Now, I know what you're thinking. Times 1, why would you write times 1? Here's why. Again, this is what I said about the busy work. I'm not doing this just to make you write that down. I want you, by the time over several days here, I want you, when you write these down, I want you to see rectangle areas in what you've written. I want you to see height times width, height times width, height times width, height times width. I want you to see that so you get imprinted here that that's an area we're looking at. Area, 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 4 rectangle areas. And then we could add those up. Of course, we know that's -8. And we know that one, -1 cubed is -1, 0 cubed is 0, and 1 cubed is 1. So even if we didn't, do you see where we can go eventually? We don't even need the graph, right? Eventually what we want to do is we don't have to draw the graph. We don't have to draw the 4 left rectangles, although we're going to in the early stages so we get a visual of that and we can do it. Our next quiz, you're going to draw some rectangles, okay? But where we eventually want to go is we want to be able to just write out this L4 approximation without a picture. So where does it start? It goes from -2 to 2, so we're going to start at the far left edge at -2. Our width is 1, so we're going to go from -2 over 1, that'd be at -1, then we'll go over 1, that'd be at 0, then we'll go over 1, that'd be at 1, and we'll stop short of the far right edge, right, because we're doing lefts. Okay? So now, without drawing them in, well, actually, it wouldn't be bad for us to draw, but we're going to draw them here in a minute, too. So let's just draw the rights real quick. So here's my first subinterval. Where would I draw my right? How would I draw my right rectangle? I'd go to the right edge, which is -1, and go backwards, right? So I'd go down, there's my height, and then it would be here. and that would be my right rectangle. So we go to the right edge for the height, across, okay? All right, what about for this one? I'd go to where? 0, and then back, across. Well, that's going to be a 0 rectangle. There's no height on that one. And then what about here? The right edge is 1. So we go up to the curve, and then back. And there's my right rectangle there. And then the last subinterval from 1 to 2, we're going to go up to 2, up to the y value, and there. And see how the blue rectangles are different then than the black the rights are different, right? So you've divided it up into those 4 subintervals. For left rectangles, you go to the left edge of each of them, go to the curve. For right rectangles, you go to the right edge. For midpoints, you go to the middle of each subinterval. And then, of course, trapezoids. We're going to do that together here in a minute. But now let's write it. We can write it without even having the picture. So what's R4? What's our first right height? F of -1 times 1 plus F of 0 times 1 plus F of 1 times 1 plus F of 2 times 1. So, and we got 4 of them. And you can see there, 4 rectangle heights and areas. Excuse me, 4 rectangle areas. Height times width, height times width, height times width, height times width. Okay? And we know -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So I guess I didn't even say this. The lefts would have a total area, what would that add up to? -8. So the lefts had an area of -8. The rights have an area of +8. Boy, those are way off. Well, you know what? When you only do 4 rectangles, you shouldn't expect to get a very accurate estimate, right? Shouldn't expect it to be great. Okay, let's do 4 midpoints. Now, I'm not even going to draw them, but I say we can write them. What is going to be my first midpoint height? It's going to be F of -1.5. It's going to be right there. F of -1.5 times, what's my width? Still 1, right? Still 1. The width of the subinterval is still 1. Plus F of, what's my next midpoint? -0.5 times 1. Plus, I'm running out of room, so I'll go down here. F of +0.5 times 1 plus F of 1.5 times 1. Now, I think we all know what the area of this one's going to be, don't we? Think about it in a minute without even plugging -1.5 in. It's going to be 0. Because this can be -1.5 cubed, which will be negative something. -0.5 cubed will be negative something, and then 0.5 cubed and 1.5 cubed will be the positive versions of those. So we're actually going to get 0. And by the way, what should be the actual area of this? Didn't we know this was going to be 0 already? I mean, we had positive and negative area, right? Okay, finally. And let me go over here. I'll do this in black again. Let's do our 4 trapezoids. Okay, now we got to think a little different about this. Because trapezoid, remember the formula? It's 1/2 times the 2 parallel heights, right? Well, what would that be for us here? It'd be F of -2 and F of -1, right? Those would be the 2 parallel sides of our trapezoid. So in here is going to be F of -1, no, -2, excuse me, plus F of -1. I didn't leave myself enough space. So F of -2 plus F of -1 times what's the height of my, or it's really the width of the trapezoid. That's this 1 right here, right? So it's 1/2, those parallel sides, and then that's 1 right there. Okay? Plus 1/2, and what would the next one be? F of my second trapezoid. F of -1 and F of 0. plus 1/2 f of 0 plus f of 1 times 1. Don't forget the times 1 at the end. And then plus finally 1/2 f of 1 plus f of 2 times 1. Now, the reason we're going to be writing these out, and we're going to emphasize writing them out, is the patterns that we see. What's going to become important for us tomorrow as we look at these is the patterns we're seeing. Okay? -2, -1, 0, 1. This one starts at -1 to 0 to 1 to 2. Then the midpoints. And then this, -2 to -1. Then we reuse -1 again, because in trapezoid, the right edge of this trapezoid is also the left edge of this trapezoid, right? So patterns and seeing patterns and stuff is going to become very important as we go through this. Okay? But from a practical standpoint, it finds these areas, right? Now, I know we could just have sat here and drawn and got our calculators and counted and saw and gotten those areas, but there's more to it. There's more at stake here, okay? Trying to see these patterns. So that's number 17. So when you do number 16, there's a lot to it. You got 4 different things, and there should be 4 different pictures with just that one alone, okay? That where we can do that one where you have to do that, okay? The other parts of our homework, each problem will be one picture and one thing that you write out, okay? All right, so let's give this a name. Now, trapezoid's kind of its own thing out here because it's a different shape than the rectangles. We have a name for rectangles, okay? And it's called a Riemann sum. So that other thing I sent you, the Riemann sum one here. Okay, how do I? This the only way is to just delete it. Okay, the Riemann sum document that I sent you. Okay, is again a little different version of the other one that I sent you. This has both left, midpoint, right, and trapezoid. But what you can do with this one is you can play around with it a little bit more as far as the different rectangles. Like right up here, you can grab this slider right here, and you can say, oh, there's 4 right rectangles, and here's a whole bunch of right rectangles. And you can slide that, and you can see that. Okay? And then you can grab this thing, and instead of left rectangles, you can drag it, and you can see midpoint rectangles. You can see right rectangles. You can see trapezoids. Okay, trapezoids just look good, right? Because they just look like they fit it well. You know, it turns out that midpoints actually fit. If you're just doing a set number of them, it turns out midpoints actually fit better than trapezoids. They just don't look quite as good. You know, in the picture. But as far as how they fit, they're actually a little better. But anyway, this is just to let you play around, visualize, you know, is really all that's about. Okay? The work we're going to need to do is going to be actually writing some of these things out. All right, so let's keep moving, and let's actually, I think, okay, we're going to write this out next. Okay? So in your notes, we're going to do this, and then we're going to get started on the homework, and we're going to actually do the first problem together. Uh-oh, I just noticed my computer is not missing some stuff at the edge here. Okay, time out. Oops. Riemann sum. All right. A Riemann sum. And let's see, is it spelled I-E or E-I? I think I spelled it E-I. This is embarrassing, especially for somebody who got third place in 5th grade at the Fillmore County Spelling Championship. All right. Maybe that's why I got third place. It's I-E. Okay. It's I-E, so it's right up here. Okay, Riemann sum. It's a German fellow, George Bernhard Riemann. So it's named for a person. Think R for rectangle, Riemann. Think rectangle, because that's what a Riemann sum is. Now this is going to be some fancy language. But you guys are in calculus, so you can handle it. Right? Let the interval AB be partitioned into n subintervals. So that's what we've been talking about. Like we've been doing 4 subintervals. So we have an interval, the total intervals from A to B. We're going to partition that, subdivide it, whatever term you want to use, into n subintervals by n plus 1 points. Now, so, right? I mean, so if I'm going to divide it into 4 points, like 0, 3, or that one we had a minute ago, from 1 to 3, we divide it into 4. Now think about it. That's 1, 1.5, 2, 2.5, 3. So if I was doing 4 subintervals, I'd have 5 values, right? The left edge and then the right edge also. So 1, 1.5, 2, 2.5, and 3. So there's always 1 extra point, right? Depending on how many you have. So that's the n plus 1. And A is the left edge. So all this means is A is going to be the left edge. We're going to call that x sub 0. Since we have n plus 1 points, we're going to start counting at 0. Right? So the last edge will be x sub 4. So in that example, 1, 1.5, 2, 2.5, and 3, that'd be your x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. That way our last one is the same as how many rectangles we have. So x sub 4 is when we have 4 rectangles. So that's why we start counting at 0. So the left edge is going to be x sub 0, which is going to be left of x1, which will be left of x2. It's just saying that's the order we're going in. So that's all that's saying. Okay? All right. Let delta x sub I be the width of the ith subinterval. First subinterval, second subinterval, third subinterval, whatever. So when we have 4 subintervals, right, we'd have delta x1, delta x2, delta x3, delta x4. Now, 99% of the time, maybe even 99.9% of the time, we will not be looking at delta x1, delta x2, and delta x3. It'll just be delta x. Because why? What was our width in that last problem? What was the width of the first subinterval?
1.
Yeah. 1. What was the next subinterval?
1.
We're going to do equal widths. We're going to divide it up so every subinterval is the same. 99.9% of the time. But what this is saying is we wouldn't have to. Wouldn't have to. We could have a skinny rectangle, then a fat rectangle, then a medium-sized rectangle, right? Like the 3 rectangles. All right. So, was that right? Goldilocks? Okay. All right. So, or they weren't fat and skinny. It was a mom and a pie. Okay, whatever. So anyway. So. What?
She was talking about it yesterday. It's so like two classes
like Adam and Eve.
never relate to
They're
each
so
other.
shit.
Sometimes do.
You know we're both born on September 9th.
Are you really?
That's
That's why.
We take senior AP classes. Wow. Been here 26 years. She's been here a little longer. Never knew. Never knew we were so close. I mean, I did know we had the same birthday, but anyway. She always brings me a P6. Someday I should get it first. All right. So let delta x sub I be the width of the I subinterval. Okay, so just say it was the width. Within each subinterval, let C sub I be the sampling point. Okay, I'll let you write that down and we'll talk about what that means. let delta x sub I equal the width of the ith subinterval. So delta x is just the width. They could be different, but for us, most times they're always going to be the same. Within each subinterval, let c sub I be the sampling point. In other words, within each subinterval, we need to pick a place, pick a point that we're going to plug into the function to get our height. We need to pick a point somewhere. Now, what are the ones I've told you about so far? Where we're going to pick, what points have we plugged into the function to get our height? Left edge, right edge, midpoint. And forget trapezoid because they're not rectangles. So technically, trapezoids are not a Riemann sum. Okay? So we've picked the left edge, we've picked the right edge, we've picked the midpoint. Could we pick some other point in there? Sure, we can pick some other point, but we don't usually. Okay, we don't. Let's just pick, let's be consistent. We'll pick the left edge every time, we'll pick the right edge every time, or we'll pick the midpoint. But we could pick other points. So that's what C is. C is just that point in there that we're going to pick to plug into the function to get our height. That's all I say. Okay, so this is all just kind of defining the terms. Okay, well then, if that's all the case, then this sum is called a Riemann sum because, of course, we're going to add them up, right? We're going to add up the rectangle areas. So that's why it's called a sum. So S sub n is a sum. So look what we got. F of C1, so that's our first sampling point. Could be the left edge, could be the right edge, could be the midpoint, or it could be some other one, but probably wouldn't be. We're going to pick some point in that first subinterval, plug it in, and get our height. And then delta x is our width. Height times width makes area. So this is the area of our first rectangle, right? Plus f of C2 times delta x2, so that's our sampling point in the next subinterval, times our width of that interval. That's the area of that one, plus dot, 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 all the way to the last subinterval. And when we add those together, that is called a Riemann sum. Okay? All right, fancy lingo, fancy terminology, just meaning adding up rectangle areas. So when you hear Riemann sum, R for rectangle, sum for add, we're adding up rectangle areas. That's what a Riemann sum is. Okay, but the fancy notation is going to be important. The fancy notation is going to come in handy when we're defining what it is we're doing, and we're trying to generalize it so we can talk about how the calculator is doing it for us, which is nice, but if you're the programmer of that calculator, you've got to know how all this stuff works, right? If you want to be an engineer, right, you've got to know how, you've got to be able to do this stuff, you've got to understand, you know, where things come from. All right. So, problem number 1 in your homework. Let's get started so you have an idea of what's going on here. So, this is homework now. Okay, I think your homework says 1 through 6, 7, 10, and 16. So 1 through 6 all have to do with this graph right here. You're going to draw this graph, I think, maybe 6 times. Yes. You're going to graph this 6 times. This particular graph. So if you want some graph paper, I've got some over here. You want some? Okay, there you go. There I go again. Why didn't I write 1 through 7? You're right. That seems silly. Okay, I know. Method to my madness. 1 through 6 all relate to this graph. Then 7 is a total separate thing. That's why I did it. But you're right. The very first time I got this book and I made up this assignment, I said, you know, I want to do 1 through 6. So I wrote it down. And let's see, what else do I want to do? I want to do number 7. So I wrote down number 7, and that's what happened. And I've never changed it since. All right. No matter how many times my classes have said, why didn't you just write 1 through 7? Okay? And there's more over here if you think you may want more. Did I not give enough?
No.
I'm sure you should just yell at me.
No. It's good to get up.
Or did Sebastian not pass it back and just kept it?
Steve asked.
Oh, you did.
Joe, did you get one? All right. So number 7, they have a graph. Now, you do not have to draw the sketch unless it says to draw the sketch. But on 1 through 6, it does. 7, it does not say to draw the sketch. So you don't have to. But they say estimate like 3 left rectangles. So I want you to write it out. On all of these, anytime you're doing a rectangle problem, and it's single digit number of rectangles, you need to write them out as we've been doing. Rectangle 1, height times width, height times width, height times width. With F notation preferable. Okay? I would prefer you to get in the habit of writing out the F value and then putting the number in. Okay? Because again, we're looking for patterns, and that's what we're leading up with this. So here's number 1. Okay, so if you want to sketch it, okay, I found a number of key points here and plotted it just to give myself kind of a rough, because you know what we're going to do here, we're going to, go into here and be drawing. Now I went every 2 units, so it was a little bit bigger graph. I made mine go, I skipped every other line just so my rectangles would be a little bigger. Okay, each one has 2 parts. Now I think part B comes before part A. It says estimate the value by evaluating a left sum with 5 equal subintervals. Draw a sketch that illustrates this sum. So to me, I would draw the sketch first, but it doesn't matter. Okay, because we don't really need the graph to be able to write out the sum. Matter of fact, probably a good idea. Matter of fact, let's try that. Let's do part A without having drawn part B here. Okay, I know some of you are still drawing your graph. Okay. But we're doing the integral from -5 to 5, g of x, this is a g graph, dx, this is a g graph. So we're going to do this total area under here from -5 to 5, right? And we're going to do a left sum with 5 subintervals. So A is L5 equals, right? So I want you to understand, without seeing the 5 left rectangles, we should be able to write this out. Okay? So, what's the first thing I need to do?
Side the intervals.
How wide are the intervals? 2 wide. Because 5 minus -5 divided by 5. Right? Be 10 divided by 5, which is 2. Now, obviously, you don't have to write all that out. I don't care. But it's good to understand it's B minus A. It's a total width. B minus A is a total width divided by how many subintervals. So each one's going to be 2 wide. So I'm going to do left rectangles. So where's my first left edge? At -5. So my height will be F of -5 times 2 plus F of, where's my next one? It's got to be at -3, right? Because they're 2 wide. So if you start at -5, the next one's going to be at -3 times 2 plus F of -1 times 2 plus F of 1 times 2 plus F of 3 times 2 plus, oh, yeah, I fooled you. I did that on purpose. Are we done? First of all, we know we're done because how many rectangles do I have here? 1, 2, 3, 4, 5. There's 5 rectangles there. That's how many I want. When you're doing left rectangles, you will not go all the way to the right edge. Okay? Your last left rectangle will be 1 width short of the far right edge. Okay? So we can now do this by just looking at these values. Let me put them in red here. So what's F of -5? Isn't it? You just look at your graph, right? It's -2. What's F of -3? Actually, I'm going to write it down. So this is -2 times 2 plus what's F of -3? Look on your graph there. Isn't it 2? It's a 2. I mean, or look at the one in your book, maybe, whatever. I don't care. But so it's 2. So that's 2 times 2. plus, what's f of negative 1? 3 times 2 plus f of 1? 0 times 2 plus f of 3? Negative 1 times 2. So we can add those up. We got negative 4 plus 4 is 0. 6 plus 0 plus negative 2. What's that? A total of 4? So we just found L5, our 5, right? So the point there in doing part A first is we could get a 4 left rectangle approximation without a picture. All we needed was the function so we could get the function value. Now we had a picture. We don't have an equation to plug into. If we had an equation for this, we could just plug into the equation. We wouldn't need any graph at all. But we're going to draw them, and here we got our y values there. So now let's go graph them.
How'd you get the y values?
F of negative 5 means go to negative 5 and get the y value. Yeah, just right off the graph. Yeah. Yeah, I'm sorry. I should have shown it. So negative 1, we go up to there. Yeah, 1. Okay? So now let's draw. So we go to negative 5 and we go down to the curve. And we go across how far?
2.
Which would be to negative 3. There's a left rectangle. It's that, don't overcomplicate the drawing of these things, right? You find your subinterval, you go to the left, since we're doing lefts, you go to the left edge, you just draw it to the curve, wherever that is, above or below or right on the axis, and then you go across, one width. And that's your rectangle. Okay, negative 3. Up to the curve, across 2, down to the x-axis. There's our next left rectangle, right? On our next quiz, you will draw at least one problem, maybe more than one. Draw a rectangle, right? And kind of like being in elementary, you can be graded on neatness, coloring within the lines, all that. Okay? So f of negative 1, so the next left edge at negative 1, up to the curve, across, and down. F of 1, that was 0. So that, there will not be a rectangle there, but I like to just kind of scribble that kind of dark there so you know that there is a rectangle with a 0 height, I guess, if you would. And then finally at 3, to the curve, across, and that's why we stop with left rectangles, we stop at 3. We stop one width short of the 5 because that takes us over to that interval. Okay? So, keep right on going. Number 2, you're going to do, I'm guessing, rights, maybe midpoints, I don't know. Nope, number 2 is going to be right rectangles. They do rights, they do midpoints, they do trapezoids, and then I think they give you a smaller interval to do. Instead of doing the whole width, they give you a smaller interval to do. So there'll be different widths than what we did here. So you're going to be drawing, you're going to be sketching on 1 through 6, and you're going to be drawing on number 16. You do not have to draw on 7 and 10. 7 and 10, they give you a picture, just like this one, but it just says to do what we did in part A. So you'll just write out like you did in part A. Okay? So you're going to write it out, but you don't have to draw a picture on 7 and 10.